is the effective interactions mostly on these supermetals at low temperature. So there are two scenarios one can think of, perhaps. One is that the metallic state becomes unstable. There's a phase transition into some kind of order state. That's the first scenario we're going to explore. And again, this is in the context of these twisted double layer, bilayer tungsten diselenide. To remind you again, there's very recent experiments from Columbia Group sees that at low temperature, the system near the filling of 1 hole per Mori unit cell becomes an insulating state. Right? It's metallic states at high temperature, but below about 10 Kelvin. There's an onset into the insulating states. This insulating state occurs in a wide range of twist angles, does not require any particular magic angle. But this insulating state is kind of fragile in the sense that a small displacement field, which changes the potential difference between the two layers. So a small displacement field can destroy this insulating state. So, according to our band structure calculations, using the continuum model developed by a McDonald's group, this is the Fermi surface right at filling n equal 1 for the twist angle of 4 degrees. The system has a bandwidth of which is about 60 milli-electron volt, which is even larger than the interaction strength. So we think that the system is far from the completely flat band limit, that the band dispersion, energy dispersion still are important. So and you can see that the Fermi surface is actually very close to a Van Hove singularity with a divergent densive state. As you further change the displacement field, you can actually you can tune the Van Hove singularity right through the Fermi level at n equal 1. So this is the advantage of 2D materials, that we can change both the filling and the band structure, right, using both top and bottom gates. And here we focus on the system at a particular filling, this n equal 1 filling, and then changing the displacement field will change the properties of the Van Hove singularity, both its energy and its characteristic. And just using symmetry based entirely on symmetry arguments, the energy dispersion near the corner of the Brillouin zone has to take this form up to third order in K. And there's an important term, which is the K cube term. And when the K squared term vanishes at a particular displacement field, you see that this Fermi surface consists of 3 straight lines intersect at a given point. Okay, so this is an example of a type 1 high order Van Hove singularity. The conventional Van Hove singularity is when 2 Fermi contours intersect each other. But in this case, we have 3 Fermi contours. For example, if you look at these blue colors here, they intersect at the same location in K space. So this high order Van Hove singularity has a topological charge which is -2, again different from conventional Van Hove singularity. It has a divergent densive state with a power law divergence instead of logarithmic, and the exponent here is -1/3. And when you move away from this special limit, that when you have a small perturbation, alpha is non-zero, then this single high order Van Hove singularity splits into 3 ordinary Van Hove singularities. But in this case, the densive state at very low energy has a logarithmic divergence. But still, when alpha is small, in the wide energy window, the densive state is approximately power law. So this splitting from high order Van Hove singularity to conventional Van Hove singularity conserves the topological charge. Because when you have the situation here, in addition to the 3 ordinary Van Hove singularity, there's also an energy extrema right at the center. So the canonical saddle point has topological charge -1, and energy extrema has topological charge +1. So the total topological charge is still -2. So you see that topological charge has to be conserved. So there's 3 saddle points, yes, at this crossing point. Yeah, each of the crossing point is a saddle point. Yes, thank you. So, so this really leads to a very simple model that if we focus on states near the Fermi level, the entire Fermi surface is really the essential part of the Fermi surface is all captured by this single dispersion in this analytical form. And in particular, when we are at the high order Van Hove singularity limit, alpha equals 0, we get power law divergence susceptibility, both in the ferromagnetic channel, Q equals 0 ferromagnetic channel, as well as in the intervalley density wave channel. Because remember, the system has two valleys, right? That's two valleys, and one valley is centered at the K point, the other valley is centered at the K prime point of the mini Brillouin zone. So, so the density state diverges at both K and K prime. So naturally, there's also a intervalley density wave susceptibility diverges with a power law exponent of -1/3. So this leads to two scenarios, two possible order states. One is ferromagnetism, the other is intervalley density wave. Now, let's remember that because of the band dispersion is pretty large, to get the ferromagnetic state, we pull all the electrons has to be in one valley. So there's a lot of cost associated with kinetic energy. On the other hand, the intervalley density wave will at least partially gap the Fermi surface, and this will gain energy. So that's why we explore this situation of the intervalley density wave. And you can actually think of this intervalley density wave as an extonic pairing between the electrons in one valley and holes in the other valley. Very similar to what Philip talked about yesterday. Yes?
So how important are these lines perfectly straight, actually?
So actually later I will show you that calculation when alpha is not equal to 0, when the lines are not perfectly straight.
Also, we add a higher order term to the dispersion, right?
That's right, yeah. But the power law divergence comes all from this third order term. So high order terms will not change the form of the power law divergence. Yeah.
And if you have the alpha, then power law would just
be cut off at a small and below a small energy. The power law divergence will be cut off.
cut off into a log? Or
Into a log, yeah, into a log, yeah. But I'll show you that what happens when alpha is non-zero, yeah. So this is just for illustration that in the particular limit, when alpha is 0, you have this Fermi surface, and the occupied states from one valley is perfectly nested with the unoccupied states of the other valley in the vicinity of these special points. And so the order parameter is this form, is electron-hole pairing. You can think of this as the analog of superconductivity. In the superconductivity, we have a pairing between up and down electrons. Here, we have pairing between spin up electrons in valley K and spin down holes in the other valley K prime. Instead of breaking the overall charge U1 symmetry, here this state breaks the U1 valley symmetry or the U1 spin SZ symmetry. Spin and valley, to remind you, are locked to each other in this system. Right, so so one interesting aspect is that in this system, because of the density state has a power law divergence, right? If we look at the gap as a function of temperature, as a function of interaction strength, or the transition temperature as a function of interaction strength, what we get is a very different from the BCS formula. If we look at this is a gap equation, there's a density state that appears here. If the density state is a constant, as in the ordinary metal, then what we find is that the superconducting gap would be exponentially small in 1 over v, e to the minus 1 over v. This is BCS formula. But here, because of density state has a power law divergence, one can simply just by dimensional scaling, one find that interaction strength, the gap here, which is an extonic gap, is a power law, goes as v to the third power when interaction strength is small. So when interaction strength becomes large, the system goes from what BCS-like limit to the BEC limit, right? And there, the gap scales as the interaction strength. Okay. And also, if you look at the transition temperature TC, again, it first increases with interaction strength when it's in the BCS limit, but then in the BEC limit, it goes down again. Okay. So this is all coming from the power law divergent density state. Now, to get back to these questions, now in real system, right, that this cubic dispersion is present, but additional perturbations are also there. There are 3 additional perturbations. First, this Van Hove singularity is not necessarily exact at the Fermi level, right? Depending on the displacement field, it's close to the Fermi level, but not exactly at it, for example. So mu is tuned by the displacement field. Only at a particular displacement field, which is about 20 millielectron volt, this mu vanishes. And also there are k-squared terms, with coefficient we call alpha. Both mu and alpha are actually pair breaking perturbations. So because if you look at this mu and alpha term, they are even functions of k, while this third order term is odd in k. So this third order term gives you perfect electron hole nesting, right? Because while these two terms, first two terms, break this perfect particle hole nesting, so they are pair breaking perturbations. On the other hand, if we apply an outer plane magnetic field, this couples to the spin through the Zeeman energy, and it shifts the electron hole bands, the hole bands of the two valleys in opposite ways because they have opposite spin. So actually, this magnetic field here is non-pair breaking to leading order.
Is it only affect the spin, or how about the valley magnetic moments? Or
Right. So that's a very good question. So so I think to odd power, right? So we can expand the effect of magnetic field in power to so the leading term is odd power term, which is opposite at the two valleys, and then next order term is the b squared term, which acts in the same way for the two valleys. So that's right. So only to in fact that is important. Yeah, only to leading order, it's the b linear term which acts oppositely in the two valleys, and that's in that sense it's pair preserving. Yeah, but if you go to the b squared term, it will be a pair breaking term. That's right. Yeah. Okay, so then so this is the full model that we work with, and in the presence of the repulsion, we again solve the gap equation, now including all these perturbations. And this is the phase diagram. This is work with Bijan at MIT. And so what is plotted on the vertical axis is, this is calculation at 0 temperature. Vertical axis is the gap. Let me remind you, this is actually the quasiparticle gap, the smallest quasiparticle gap in the system, so which is what you measure in activation behavior of the transport. And this x-axis are the different perturbations. The first term is the energy deviation from the Fermi surface, the energy of the Van Hove singularity away from the Fermi surface. And you see that there is a first order transition at small alpha. Okay, well, small alpha, there's a first order transition. But you can see that this alpha term, this perturbation, as well as the chemical potential mu. So the different colors are representing a different alpha, right? Different alpha. So one thing you notice is that this extone insulating state is very fragile against displacement field, right? A small displacement field which moves the energy of the Van Hove even like 1% of the bandwidth, right? Deviation of the energy of the Van Hove point from the Fermi level of about 1% of the bandwidth is sufficient to destroy this extone insulating state. And on the other hand, if we look at the magnetic field dependence, that this extone insulating states can survive into a much larger range of magnetic field. So here, this x-axis is the Zeeman energy, again measured in terms of the bandwidth. So up to a few percent of the bandwidth, the insulating state is still robust. So this explains the sensitivity of the insulating state to the displacement field, and it further predicts that it should be relatively robust against magnetic field.
What
yes?
is the underlying reason for this sensitivity to the displacement field? Because it seems that it's like a diagonal term. So
it's because it's pair breaking. So what happens here is that mu, the chemical potential mu maps to the Zeeman field in a real superconductor. So we know that in a real superconductor, applying the Zeeman field causes a first order transition from superconducting back to normal. So this is exactly the analog of that.
Or it makes one pocket bigger, the other smaller.
That's right. It destroys nesting. Yeah, exactly. Yeah. Right. Okay. And our proposal then is that this insulating state in twisted WSE2 is Intervalley coherent state. So it's electrically insulating, but because this state breaks the spin U1 symmetry, it's actually a spin superfluid. very similar to this, what Philip talked about yesterday, this excitonic superfluid in the quantum Hall bilayers. The whole system is electrically insulating, but it's a superfluid in the counterflow channel. So here, the analog of layer degrees of freedom is valley or spin, right? Which are one and same thing here. It's locked to each other. So then what we would expect is some kind of a superfluidity of the spins. And this is our proposal how to measure this. If we use circularly polarized light, one can actually generate a net spin polarization in tungsten diselenide. And this has already been experimentally demonstrated last year from Feng Wang's group, not in twisted WSE2, but in a single layer WSE2. And this spin polarization then can diffuse, right? Diffuse, and by further using circular polarized light, one can actually detect the spin polarization at different spatial locations. So what his group developed is a very remarkable spatial and time-resolved measurement of the spin polarization, okay, at a given location at a given time. So he can really essentially watch the dynamics of the spin degrees of freedom. Now, in the usual case, if you have just spin diffusion, then these two equations, coupled equations, describe the spin dynamics. The decay of the SZ, spin SZ, is given by a current of the spin current, as well as this second term describes the spin relaxation due to, for example, electron photon scattering, due to the spin orbit interaction, etc. But the important term is this spin current term. So in a normal metal, the spin current is purely a diffusive current, so it's proportional to the gradient of the spin density. So when you combine these two equations, you find that the spin, when you first at time t equals 0, you use circular polarized light to create a spin imbalance at, let's say, x equals 0, and then it just diffuses away, right? So at any later time, the spin density is still peaked at x equals 0, right? But on the other hand, if the system becomes a spin superfluid, right, despite being electrically insulating, the spins can propagate ballistically. So in that case, the spin current is proportional to the gradient of the phase, right? And the time derivative of the phase is equal to the spin density. This is very much just like the Joule-Suzanne relation of the superconductor, right? So when you now take this coupled set of equations, and this is what you get, that once you populate a spin at time t equals 0, at x equals 0, the excess spin actually moves to the left side and to the right side, right? There's a ballistic spin propagation. So this, we think, is a way to detect the spin superfluidity, which is the analog of this counterflow in the bilayer system. Okay.
Do I understand that the only way you account for spin orbit is through relaxation?
So actually, so in this system, let me make it clear. So there is an Ising spin orbit interaction which locks the spin to the valleys. That is already accounted for here. But this MZ, so in other words, in the pure Ising system, the SZ is still conserved, right? So what this extra term represents is like additional, for example, with disorder would break the SZ conservation, right? So this, all this relaxation represents additional terms that accounts for the breaking of the SZ conservation. So this in this monolayer WSE2, for example, his group, Feng Wang's group, has already shown that this spin relaxation time is relatively long, so he can really image this spin decay. Yeah. So hopefully the similar set of experiment can be done on these WSE2 bilayers, and then our prediction is that in these insulating states, you will see some very different behavior in the spin transport.
Did you account for the orbital magnetic moment in your theory?
Sorry, again?
Did you account for the orbital magnetic moment in your theory?
I think all this is captured because, again, the spin is locked to the valleys, right? So, spin angular momentum, orbital angular momentum, they're all represented by sort of SZ here. Yeah. Okay, so let me now move on to twisted bilayer graphene very briefly. So again, our motivation is that from very early days that STM experiment has shown that there are these Van Hove singularities in the Maury bands of twisted bilayer graphene. So, so how would this Van Hove singularity change when the twist angle is near the magic one? So, so we noticed that at relatively large twist angles, right, the Van Hove singularities are along the gamma m direction, and there are 3 Van Hove singularities in the Maury band from one valley. So again, because the 2 valleys are decoupled at the single particle level, we just plot the dispersion and the Fermi contours in one valley. On the other hand, in our calculation, we noted that when the twist angle is close to 1 degree, you actually get 6 Van Hove singularities, which are away from the gamma m direction. So as a function of the twist angle, then somewhere in the middle, one of the saddle points here must split into 2, right, in order to conserve the total topological charge. So this leads us to this is how we are led to this concept of high order Van Hove singularity. So again, we can understand this behavior, the splitting from a single saddle point into 2 saddle points, by just looking at the energy dispersion around the critical point on the gamma m line. So again, the 2 leading order, there are these k squared terms, but to the next order, there's a term which is kx ky squared. So kx is along the gamma m direction, ky is perpendicular, and this term is allowed by the reflection symmetry around this gamma m line. And once we include this high order dispersion, we can now look at how the energy contour evolves with this coefficient beta, right? So when beta is positive, we get an ordinary saddle points, while when, on the other hand, when beta is negative, k equals 0 now turns into an energy extrema, right? At the k equals 0, instead of a saddle point, you have energy extrema, but 2 additional saddle points appear, right, next to it. And so we end up with 2 saddle points plus 1 energy extrema. And again, the total topological charge of -1 is conserved because the saddle points carry topological charge -1, and energy extrema carries topological charge +1. Right at beta equals 0, what we see is that the dispersion is very interesting. They have 2 Fermi contours that touch each other tangentially, right? So this again leads to a high order Van Hove singularity. Okay, that it's defined by a dispersion which involves high order terms as the lowest order term. Okay, so so then all this is we can infer this behavior purely from just this polynomial, right? And then we went back to look for the particular twist angle, and indeed we find that at this around 1.1 degrees, and we see that the Fermi contours is shown here. It consists of 2 lines that touch each other almost tangentially. Okay, so again, I want to emphasize that here, this high order Van Hove singularity is realized by tuning a single parameter, which is twist angle. And when we look at the tensor states for this dispersion shown here, that in addition to this k to the 3rd power term, it turns out that you can also include the ky to the 4th term, and these 2 terms actually have the same scaling. Okay, in this way. Okay, the kx has a scaling dimension of energy to the power of 1/2. Ky has a dimension of energy to the 1/4. So then both terms have the same units of energy, so they should both be included. But including this extra term doesn't change the fact that the 2 Fermi contours touch each other tangentially. So this is a defining property of this high order Van Hove singularities of this type. We call it type 2. And again, if you look at just the dimensionality analysis, the tensor state will diverge with the power law. Now the exponent is -1/4. Now here, another interesting feature appears. So in the previous example, where we have 3 Fermi lines intersect at a single point, the divergence is a power law, but it's symmetric. At positive energy and negative energy, the tensor state is symmetric. But here, this tensor state has a very strong asymmetry. Right? The prefactor differs by a square root of 2 on one side and on the other side. So, so this is another a new feature of this high order Hove singularity. And again, I want to emphasize that even when the beta is not exactly 0, the tensor state is approximately power law in a wide energy range, but below a small energy cutoff, it changes from power law divergence to logarithmic divergence. And this is the full densive stage as a function of beta, okay, as shown here. So then we can look at, yes?
This transition with respect to beta, this only happens when you change from beta from negative to positive?
That's right.
So it's only dependent on beta?
Only depend on beta, yes, exactly. Yeah. So by tuning a single parameter, you can.
Because all those two parameters, they should be dependent on the magic angle in a self-consistent way.
Oh yeah, absolutely. All these coefficients depend on twist angle, right? But the important one is this beta. Yeah, absolutely. Yeah.
And it doesn't matter if alpha and gamma are positive or negative, there's no restriction yet.
So here I'm assuming that alpha is positive. The sign of gamma doesn't matter. Yeah. But the important thing is that when alpha and beta are of the same sign defining this way, you get a ordinary Van Hove singularity, one Van Hove singularity. When alpha and beta are of opposite sign, you get two ordinary Van Hove singularity. When beta is 0, you get a high order. Yeah. So, right. So now, is this really relevant to the real experiments? So, there's recent experiments from the Columbia group, the STM experiments. There are several STM experiments. I'm showing the Columbia data here. And you can see that these are the differential conductance, DIDV, at different twist angles. So if I don't show you the twist angle here and ask you, which one is at the magic angle, right? You might have a hard time because just looking at these densive states, right? The overall energy scale seems to be decreasing monotonously, right? For example, the Van Hove peak are even closer to the Fermi energy at 0.79 degrees, right? So, but what's interesting that when we analyze this data, we obtain this data and we did our own data analysis. And these are at 3 different twist angles, about 2.2 degree, 1.1 degree, and 0.79 degree. So this is a zooming in of the DIDV data. Now it's in a much smaller energy window, right, near the charging neutrality point. And the first thing you notice that although Van Hove singularity exists at every twist angle, you notice that something very interesting happens, that at this magic angle, this Van Hove singularity is strongly asymmetric with respect to the center of the peak, right? Both above this 1.1 degree and below the 1.1 degree, the Van Hove peak is approximately particle symmetric with respect to the center, but it becomes extremely skewed right at the magic angle. So then we actually fitted the densive state using the expression that I just given you, which includes both the special limit beta equals 0, and when beta is non-zero, we have a Noah Yuan derived an analytical formula for the complete general case. So we can actually use this to make a fitting, and these solid lines are the densive state from analytical calculation. And you can see it fits very well. And from this fitting, we can infer this small energy cutoff, right? And remember that when the energy is above this cutoff, you can treat the dispersion as approximately a power law, right? So the smaller this energy cutoff is, the closer the system is to the high order Van Hove singularity limit. And you see that at 1.1 degree, this energy W becomes very small, becomes close to 0. Okay, there's non-monotonous change of this W. So again, this tells us that on 1.1 degree, the system is close to a high order Van Hove singularity. And one of the defining feature is this, of this high order Van Hove singularity is a power law densive states. So here I'm plotting the raw data, the densive states in the vicinity of this peak, and as a function of energy. And you see that over some energy range, it indeed has this power law dependence with this exponent, minus 1/4. Yeah. Okay, so of course the interesting question is, what happens when you dope the system close to the Van Hove singularity, and that we are still studying this problem more carefully. And I just want to mention that there are a lot of interesting physics in twisted bilayer graphene, and some aspect of it appears to be more dominated by strong coupling physics, while in some of these new devices, it seems that the single particle effects are actually more important. So for example, this is work from the Hove's group very recently. And this is a device where the twisted battle graphene is relatively close to the metallic gates. The distance is 7 nanometers. And in this device, for example, this is the temperature, the x-axis is density, and there's no insulating states at any density. So if you look at the resistance as a function of density for different temperatures, at all temperatures, at all densities, the resistance decreases as you lower the temperature. So there's no insulating states at all, and yet superconductivity, superconducting dome are still present. So we are currently thinking about the relevance of Van Hove singularity to, for example, this type of device. And another interesting hint is that if you look at the Hall carrier density measured from experiments in this device, it has a very interesting behavior. To remind you that the Hall coefficient, right, is the voltage divided by the transverse current, and further divided by the magnetic field. So in a simple system, right, then the Hall coefficient is inversely proportional to the charge density. Okay, so people define this inverse of the Hall coefficient in terms of the Hall density, and indeed at near charge neutrality, the Hall density is equal to the carrier density. But as you see that as the system starts to approach this filling around 1.7, it strongly deviates. From the actual carrier density. So this may very well be related to the Van Hove singularity near this particular filling. As you see, this is the band stretcher calculation, and this Van Hove singularity, high order Van Hove singularity appears right here when you see the two Fermi contours touch each other tangentially. Okay, so this is a summary of the first part of the lecture. Any questions? Yes?
How do you define momentum space, the cutoff for your low energy theory in your interest?
That's an excellent question. So I didn't have time to talk too much about it, but yeah. So in all these cases of high order Van Hove singularity, when I say the standstill state has a power law divergence, this divergence all come from the vicinity of k equals 0. So when I perform that integral, I extend the momentum cutoff, the UV cutoff to infinity, and the integral is still convergent. So this is very different from the ordinary Van Hove singularity. Ordinary Van Hove singularity, right? It's a logarithmic divergence. It needs both. It needs a UV cutoff as well. So this is why, in the case of the high order Van Hove singularity, we don't need a UV cutoff. So all the divergence all purely come from IR, from the vicinity of k equals 0. And this actually has a very important implications for the next part of my talk. Yeah. Yes.
When you feed that is such that you have a higher order Van Hove singularity is essentially to the point of the Lipschitz transition between states when you have 2 points and then they merge with 1.
Absolutely.
You're exactly the transition line, so how robust it is. Although it's Lipschitz transition, it's still a transition.
Yeah, so all these high order Van Hove singularity requires tuning parameters, tuning one extra parameter.
Sure.
So here what I'm showing is that at the, but we should not be afraid of tuning. That's my message. that there are so many experimental knobs that one can play with, right? Density, twist angle, electric field. There are sufficient tuning parameters. So for example, here, for example, at this particular parameter, right? And we see that the two contours are almost exactly tangentially touching. Now, maybe for this particular example, it's not exactly right there. But you see that the physics at a broad energy range should not depend on a small deviation away from it. Right? That's, in other words, the way I will put it is that if you look at the density state, it has a power law divergence, but maybe at a very small energy cutoff below that, it changes from power law to logarithmic. Right? So that's the way you can think about it. But if the physics already happens, interesting physics, if it already happens at temperatures above this energy scale, then it can treat it as a high order Van Hove singularity. It's very much like looking for quantum critical, for general critical phenomena. The critical phenomena requires tuning. Yeah. So here, I like to think that at least at the single particle level, that the magic angle is a special angle where the Van Hove singularity turns into a higher order Van Hove singularity. That's just one. Yes.
From this plot of coefficient,
Yeah, we are working on that. Yeah, we are working on that. Yeah, it's a very good question. Yeah. Yes.
So how, I mean, you mentioned in the last lectures already, but how robust is the stories against the relaxation, atomic relaxation?
Well, that just changes the particular angle where this physics happens.
But topology
Topology won't change. Exactly. Yeah.
In the same way, probably some of the strain effects.
Absolutely. Absolutely. Yeah. It just changes the details, but without changing the. That's the important thing, that all these critical points are topological objects. That's what I want to emphasize. And that when a saddle point splits into two saddle points, right at that transition point, you get a high order Van Hoff singularity. When three saddle points merge together, again, at that transition point, you get a high order Van Hoff singularity.
However, I can imagine that if I, for example, the Unix strain,
right.
So if I just kind of stress kind of the lattice quite a bit, at some point, some critical change may happen, and kind of band topological changes also? Is it possible?
Yeah, but again, the existence of saddle points itself is extremely robust. For any isolated energy bands, there has to be at least two saddle points, according to this general theorem, right? There's total winding number has to be 0 on the torus.
But what if the other band moves around?
Right. That's
new overlaps.
Right. So yeah. So that's why this requires defining isolated bands. So as long when bands are isolated, you can get these saddle points. Yeah. Right. Okay. So now let me move on to the last part of this talk. So now I've described cases where for systems with power law divergent tensor states, that in several different systems, in WSC2, in twisted parallel graphene, and in WSC2, for example, we show that at low temperature, interaction drives the system into an ordered state. For twisted parallel graphene, because the system has 6 Van Hoff singularities, it's much more complicated. So I'm not going to say too much about that. But instead, here we want to ask a purely theoretical question, right? So is it possible that for systems with this power law divergent tensor state, could it remain metallic down to the lowest temperature, down to the 0 temperature, without any long-range order, right? So I'll show that this possibility can indeed be realized. So here, let me emphasize that there are actually two competing effects, let's say, two competing scenarios one can think of when the tensor state is very large. So on the one hand, when you have when we have a large tensor state near the Fermi level with repulsive interactions, the system may develop, let's say, a stoner ferromagnetism, so that after this magnetic order sets in, the tensor state splits into two peaks, one for spin up, one for spin down, and these two peaks are now moving away from the Fermi level. So this transition basically lowers the tensor state at the Fermi level, and potentially it can gain energy. Right? So this is one scenario. But on the other hand, there's another scenario that I think needs to be considered. And by the way, let me first say that in a system with complete flat band, right, then this is essentially the only scenario, right? This is the scenario that leads to the quantum Hall ferromagnetism. If you have, one out of 4 degenerate lambda levels occupied, very often the system spontaneously become polarized. All electrons occupy one component. But in the system I'm describing, there is a divergent tensor state, but only at the Fermi level. The full bandwidth is still finite. Okay, and I'm in fact going to deal with a limit where the interaction is small compared to the full bandwidth. Right. So I'm always working in that limit. So in this case, there's a screening effect, okay? Because there is a finite and large bandwidth, electrons actually can move apart from each other. They are mobile, and by moving apart from each other, they can, roughly speaking, they can lower their repulsion. So this is essentially the screening. So when you have large tensor state, actually screening lengths become even smaller. So one might think that screening essentially weakens the effect of interaction, and this reduction is most effective when you have a large tensor state near the Fermi level. So maybe the system flows back to some Fermi liquid. So it turned out it's exactly the balance between these two competing effects that the system flows into a non-Fermi liquid. So now we're going to deal with this particular model. Just to illustrate, we're going to work with systems which has only a single high-order Van Hoff singularity at the Fermi level. And just to give a concrete realization, consider a tie binding model of electrons on a square lattice but with anisotropic hopping in the x and y direction. So in addition to the first neighbor interaction, let's add another second neighbor interaction in the y direction. And again, the details doesn't matter, but I just want to illustrate, use this model to illustrate that for a particular choice of parameters, right, as you tune just a single parameter, you can have a Van Hove singularity that turns into a high order Van Hove singularity at the boundary of the Brillouin zone. So the dispersion is kx squared in one direction and is quadratic in the other direction. So this tensor state now leads to a power law divergence with exponent again -1/4. So right, so again, this shows how the Fermi surface at Van Hove singularity evolves. When the beta is positive, we have ordinary Van Hove singularity with log divergence. When beta is 0, we have two Fermi surfaces touch tangentially, get a power law divergence. And when beta is negative, two ordinary Van Hove singularity develops. So, when we further add the electron interactions, this is the full model we're going to study. Now, so the first term describes the kinetic energy, which is kx squared, ky to the 4th. Mu is the chemical potential. And the second term is a short-range contact interaction. Now, if you look at this model, one of the appealing aspects, at least to me, is that here the Fermi surface is completely scale invariant. Right? There is no characteristic Fermi momentum anymore. Right? So remember that in the first lecture I described, in the ordinary metal, right, there's always a characteristic scale, which is the Fermi wavelength, Fermi momentum kf. Right? But if you look at, and this has to be the case for any macroscopic model. Right? For any macroscopic model, there's always a characteristic size of the Fermi surface. And that is what makes the theory of metals challenging, because we have to deal with many, many low energy degrees of freedom. Okay? However, if you look at systems with a Van Hove singularity, okay, although the full Brillouin zone, in the full Brillouin zone, there's still a finite Fermi surface. The density state divergence only comes from the vicinity of special points. And then we can actually, this motivates us to deal with a continuum theory that only describes the vicinity of these points. And in the case of the high order Van Hove singularity, I'll show that this approach is both feasible and leads to a control theory of non-Fermi liquid. Yes?
I think this absence of the scale is the particular property of your model that only has one high order Van Hove point.
Correct,
if
correct.
You have more than one, you have two KF that connect
Right.
these.
So actually, if you have two high order Van Hove singularities, what you do is that you introduce additional flavors. Yeah, you introduce additional flavors. But there are additional scattering processes which transfer electrons from one to the other. That's right. But indeed, it turned out that we tried many cases, and only this case with a single high order Van Hove singularity, within the cases we found, leads to a non-Fermi liquid state. Yeah, that's right. So, right. So basically, let me just emphasize again that the sort of the philosophy what we are doing here is that in metals there's a finite Fermi surface. In principle, every point on the Fermi surface can lead to gapless excitations. However, when you have a divergent tensor state in the vicinity of a point, that point is more special. Right? That point is more special. In other words, a single point outweighs other parts of the Fermi surface. Okay, and or the vicinity of that point outweighs the rest of the Fermi surface. So this motivates us to look at this model, which has no characteristic scales in the Fermi. This model has a Fermi surface, right, that actually extends to infinity. So this is related to the earlier question. So when we compute the Nansen states, we do not impose any momentum UV cutoff. So in this model, there's a full Fermi surface that extends to infinity. But the divergent tensor state only comes from the vicinity of k equals 0. Yes, Sri? Absolutely. Absolutely. I'll talk about that. Yeah. So the punchline is that you have to tune. You have to tune extra parameter.
So you tune that and U and G?
No. You don't need to tune G. That's the key part. Okay. Yeah. So you tune, in the end, two parameters. Yeah. One is basically the coefficient of the ky squared term. The other is mu. Yeah. But G will flow to a fixed point. So this is very much analogous to the phi 4 theory. for classical IC model, for example, right? The Wilson-Fisher 5-4 theory. In the 5-4 theory, you have a quadratic term, right? Kx squared plus ky squared. You have a detuning from the phase transition point R, which is like the mu here. And then you have a nonlinear term, 5-4 term, which is the analog of the interaction term. So, so again, let me just skip this. This is density state divergence. And now to do this RG analysis, we want to introduce a small parameter, right, to control the new fixed point. And here we use this dimensional expansion. So the problem we are really interested in 2 dimensions with dispersion kx squared in one direction, k fourth in the other direction. But let me extend the problem into d dimensions. In one direction, the dispersion is k squared. In the other d minus 1 dimensions, the dispersion is quadratic. And this leads to the following expression of the density states that's shown here. And it has a power law divergence with exponent epsilon, which is shown here. 3 minus d divided by 4. In 2 dimensions, the exponent is 1/4. Okay, it's a problem we are interested in. But we are going to treat epsilon as a small parameter, which means that we are looking at 3 dimensions that are slightly below 3 dimensions. And also, you know, for people that are interested in these technical parts, if you are at the limit epsilon go to 0, the power law divergent density state actually turns into a logarithmic divergent density state. And I can say more about this later if you're interested. Okay, so let me first, you know, look at the mean field phase diagram, right? So when you turn on interactions, what happens is that without interaction, the system changes as a function of chemical potential. It goes to a Lifshitz transition. The Fermi surface changes from hole-like to electron-like. But with interactions, there's an intermediate ferromagnetic state, right? And, you know, again, this is not surprising because this is basically Stoner theory of ferromagnetism in this mean field approach. And here, you know, no matter how small the interaction is, there's always some intervening ferromagnetic states. That's because density state diverges. Okay. And let me now again write all these interaction strengths and density and chemical potential in terms of dimensionless parameters. So we introduce an energy, UV energy cutoff, which I call lambda, and the interaction is measured in terms of the density state at the UV energy cutoff. Okay. And this is basically what happens that all these transitions here are first order, right? From the transition from the whole Fermi liquid to the ferromagnetic state, the transition from the electron side, they're both first order transition. But the first order transition get weaker and weaker as you go to the weak interaction limit. Okay. So now let's ask, you know, how is so this is a mean field result. So we expect that the mean field result is qualitatively correct when the interaction is not too small, because in the first order transition there is a finite correlation length. So fluctuations should not change first order transition too much. But when the interaction is very weak, the first order transition in mean field theory become weaker and weaker. So in this weak interaction regime, we expect fluctuation become dominant, and we need to do a more careful analysis. So this is what we do with the RG, and this is a procedure. So we start with a theory which has one energy cutoff, I call lambda, and then we progressively integrate the modes that lies in the energy range of lambda and lambda prime, and then we try to rescale the fields and rescale the parameters so that the theory goes back, the energy cutoff goes back to lambda, and after this process, the parameters would have been changed, and we keep track of the flow of these parameters as we keep doing this. So, so this is very much like the case of the 5-4 theory, right, for Wilson-Fisher theory. And I want to emphasize that again. You notice that when we impose an energy cutoff, right, basically all the states we're dealing with are still living in a two-dimensional momentum space, and you know, there's always a finite Fermi surface in this problem. Okay. So there's a UV cutoff we impose. Right? The lambda is a UV cutoff. In this problem, the theory is really specified by this action. This action here, together with energy cutoff, which represents the bandwidth.
But your lambda is supposed to be of the order of bandwidth?
It's supposed to be of order bandwidth, yes, correct. Or to be more precise, lambda, the bare lambda we work with is the range over which the density state is still approximately power law.
Which is much less than your bandwidth.
Say again?
Isn't that much less than your bandwidth?
It could be, it's usually of order bandwidth. Yeah. I mean, that depends on microscopy model, but for example, in the case of the tungsten diselenide, that is of order of the bandwidth. Yeah.
And when you say G is strong or weak, you mean
G is much smaller. Yeah, actually, yeah, it's good. Then okay, good. So this is right. So there is a dimensionless parameter which is written here. G is the bare interaction, contact interaction. Lambda is the energy cutoff on the order of bandwidth. D is the density state at that energy cutoff. So we require that I'm always going to work in this regime when this dimensionless parameter of interaction is much smaller than 1. So this is a regime that the theory is controlled. Okay, so at the tree level, if you perform this RG analysis, you find that the chemical potential is relevant, and the contact interaction is barely relevant. It's relevant, but the scaling dimension is only very small. It's of order epsilon. Epsilon is the density state exponent. All additional interactions, right, which involve some spatial derivatives, would be irrelevant. So again, this is the advantage here. Remember that in the Fermi liquid theory, right, you deal with a full Fermi surface. There are infinite of these lambda parameters in every angular momentum channel. But in this theory, only one interaction, the contact interaction, is a relevant one.
I want to go back to Sherry's comment before.
Yeah.
So about dynamically generating this
Yeah.
KY square terms, right? Don't you need to include some counter terms?
Yes, absolutely. So I'll show you that. Yeah. So you should include that. Yeah. Here I'm just using Yeah. What happens is that basically, in one loop level, it's not generated. But if you go beyond one loop, we expect it will be generated. But we always need to tune a parameter so that we are at this point. So yeah. So I'm running a little bit late. So let me just quickly mention that in the one loop calculation, there's only these two diagrams that needs to be taken into account. And again, in general, that if you do the RG, the coupling, initially we have a contact interaction, right, which is a completely local. In principle, higher finite range interaction can be generated. But again, because there's only all these high order finite range interactions are irrelevant in the RG sense, in the end, we only need to take into account we can expand basically this diagram in terms of the momentum of the incoming states, and only to leading order, we need that into account. Essentially, what this is saying that all we need is to look at the vicinity of this Hove singularity, and so the final result is the following: of the two contributions to the renormalization of the interactions, the particle-particle channel, okay, give you a finite contribution, and what this is saying is that there's this BCS process, which leads to basically decreases repulsive interactions. So the final result is shown here. The flow of the interaction, at the tree level, there's an epsilon times G term, but at the quadratic level, there's a G squared term with a negative coefficient. So this leads to a new fixed point, which is at finite interaction strength, and also the critical chemical potential is shifted from the non-interacting case. So it's in full analog with the 5-4 theory. The chemical potential plays a role of temperature. The non-interacting supermetal corresponds to the Gaussian fixed point when the interaction strength is 0. And this new fixed point is the analog of the Wilson-Fisher fixed point. Yes?
The RG equation looks like it has
Some
it looks like has
loop diagrams.
Logarithm diagram.
Log, yeah.
And is there some special point from the higher order out of singularity? Because if we have just normal out of singularity, then the diagonality is log square, but it looks like just has
So I think the high orderness of the Van Hove point is already included in this
Tree level.
scaling.
The tree level, yeah. The tree level. So So this part, the first term, the tree-level part, this comes from the high-order van Hove singularity. This term, epsilon, is an exponent of the density state divergence.
The fact that he's scaling kx and ky differently, that's a high order.
Yeah, exactly. Yeah. Okay, so putting all this together, okay, what it means is that, and also emphasize that this new fixed point we find, right, is when the interaction strength is of order epsilon, much smaller than 1. So that's why this is a controlled calculation. So combining this with a mean field phase diagram, what we showed is that when interaction is weak, okay, instead of having a ferromagnetic region in the middle, there's a line of here which separates the electron and the whole Fermi liquid, right? And this line, the line is controlled by a interacting fixed point. This is an interacting supermetal. Okay, and later I'll show this is a non-Fermi liquid. So the point is that so this supermetal really is a state that is intermediate between the electron Fermi liquid, whole Fermi liquid, and the ferromagnetic states. So the end of this line is partly a speculation. So this end of this line is when interaction becomes sufficiently strong, but one natural speculation here is that this line joins this ferromagnetic region. Yeah, yes, Sri? That's actually right. I'll talk about that later. Yeah. So in other parts, in other words, at this special point, I have a full Fermi surface, right? In the vicinity of k equals 0, the quasiparticle weight vanishes. But in other parts of the Fermi surface, we believe there are still well-defined quasiparticles.
So it's essentially still Fermi liquid.
No. But at the high order, at the k equals 0, at that point, it's the quasiparticle weight vanishes.
Yeah.
But that point is very special because all the thermodynamic properties, like specific heat, is governed by the vicinity of this point. Yeah. Okay, good. Yeah, and also back to Shri's question. So indeed, that everything I've described here so far is for one loop. What happens if you go beyond one loop? The most important part is the following: that although the ky squared term we set it to be 0 at the bare level, it in principle would be generated when we go to beyond one loop. And this means that we actually have to tune the system with an additional knob, right? We need to tune the chemical potential mu, but we also need to tune the coefficient of the k squared term, what Yuxuan calls the counter term. We have to adjust the bare values of the ky squared term to stay at this supermetal state. So this supermetal state, really interacting supermetal state at 0 temperature, is in that sense a multi-critical point, requires tuning 2 parameters. One is the feeling, the other is, for example, a critical displacement field. Okay, so we need more tuning. And just if I'm just 2 minutes, yeah. So now, to what extent this is a non-Fermi liquid? So if we look at, for example, the charge and the spin susceptibilities, they diverge, and the divergence with the exponent can be inferred from the scaling dimension of these operators. To one loop level, the charge and the spin susceptibility diverge, as well as the specific heat C over T diverge, all with the same exponent as a non-interacting case. Okay. However, the pairing susceptibility does not diverge. The pairing susceptibility in the non-interacting limit, the pairing susceptibility also diverges with the same exponent, but with interactions, it does not diverge. Again, this is exactly what happens in 1D Lagrange liquid. In the 1D Lagrange liquid, if you look at the density response along wavelengths, it has exactly the same power law decay 1 over x squared as a non-interacting case. But the pairing susceptibility diverges has a power law divergence, which has the pair-pair correlation function in the 1D Lagrange liquid has a different power law exponent. So this is exactly like that. Okay, and also again regarding to the quasiparticle weight, so this requires us to directly look at the fermion correlation function, the single particle Green's function, and this actually requires a 2-loop calculation, and this is really work by Hiroki Isobe, and I'm just showing the result that using the field theory technique, he was able to show that the fermion, the single particle Green's function has a power law decay, but with an exponent that is different from the non-interacting case. Okay, this new exponent is epsilon plus a correction, which is a order epsilon squared. Okay, and this is direct shows directly that the system is non-Fermi liquid. Again, very much like the Lagrange liquid. And I think, right, let me just come to the end. Just to summarize that the second part of this talk, I've described a situation where we start with a non-interacting supermetal with power law divergent densive state. We add interactions. The system actually flows into a non-Fermi liquid. And this is a controlled analysis involving a small parameter. And although there is a full Fermi surface, the relevance or irrelevance of a given operator is determined by the vicinity of a special point, okay, where the densive state diverges. And again, as Sri said, what we expect is that the vicinity of the k equals 0, the quasiparticle weight vanishes. But other part of the Fermi surface, they are well-defined quasiparticles. Okay, so this leads me to this sort of summary, speculation. Let's say, we over the last, let's say, 15 years, right, starting from graphene, there's a lot of interesting developments about semi-metals. Not only they are interesting for their own sake, as Philip said, the Dirac fluids, hydrodynamic regime, but also Dirac points is in some sense, a mother state of many other interesting states of matter, such as topological insular, topological superconductor. Perhaps, right, metals with divergent densive state in the vicinity of a point, this kind of a supermetal can be a useful starting point for studying correlated electron states. Thank you. Oh, because it's analog with with semi-metal. Semi-metal has a vanishing densive state at the Fermi level. What about states with divergent densive state? So for the lack of a better name, we just call it a supermetal.
So what is the transfer property?
Yeah, that's an excellent question. That's something we are actively studying now. It's non-trivial in the following sense, that although you have a divergent densive state, right, which you might think that dominates the transport like resistivity, but in the vicinity of this point, the velocity also goes to 0. So it's actually unclear whether these regions directly contribute to electroconductivity. However, one scenario we are currently studying is imagine that the system also has a high order Van Hove singularity, right, in one part of the Fermi surface, and the other parts of the Fermi surface which has fast electrons with large velocity. And these two type of pockets can interact with each other in a non-trivial way. And we are now trying to understand whether this can lead to interesting behavior of resistivity.
Usually that will suppress the conductions quite a bit.
That's right, that's right, yeah.
So unlike the names,
Yeah.
I think likely that becomes core metal.
Exactly, I totally agree. So in fact, that one of the motivations for me to look at this is the following. Let me show you this, what I talked about briefly in the first lecture. I totally agree, Philip. Of course, we never thought about this when we come up with a name. So that's always the case. Right, so this is the case of an niobium tin, right? So last time I showed that this material actually has a power law divergent densive state near the Fermi level, unknown before. If you look at the resistivity, right, it has a very non-trivial behavior, right? People will talk a lot about linear T resistivity, but this is actually sublinear, right? In a wide temperature range, this resistivity looks sublinear. So, could this be related to power law divergent densive state? So this is something we are still struggling with. Yeah, I thought I would have something to say, but no.
Let me just ask a very simple question.
Yeah.
So you have the whole Fermi surface and two Van Hove points.
Right.
So you're saying if you only restrict your theory around these two Van Hove points, there's inherent susceptibility is finite.
It's finite, right? Right.
But what about the remaining
Correct.
Fermi
Yeah.
surface?
That's correct. So the other part may still have superconducting.
Right. It can get the Kohn-Lehtinger type superconductivity from the rest.
Correct. Yeah, correct. Yeah, I agree. Yeah.
Is that possible to induce some kind of divergence in the denser state by turning on interaction in semi-metal or something like that?
Yeah, so yeah, that's an excellent question. So, so I think what you're asking is the following, so here I pursued the scenario where the band structure level give you divergent tensile state. Now, what if we take an ordinary metal, right, with strong interactions? I mean, sure. For example, if you think about a metal that is becoming nearly ferromagnetic, then the spin susceptibility will diverge, right? So what I do not know, and I'm sure there are many experts here that are much better than me, is that what about the charge compressibility? What about the C over T? Does it also diverge with the same exponent at the ferromagnetic critical point? Right. This is a question that maybe the experts, I'm sure. Yeah, I don't know the answer to that question. Now, what's interesting about the supermetal is that already at the non-interacting level, you see that all the susceptibilities diverge with the same exponent. And when you turn on interactions, this supermetal interacting fixed point, charge spin susceptibilities still diverge to one loop level with the same exponent, but the pairing susceptibility now is non-divergent. Right? So to what extent like other critical point share this feature is an interesting question. I don't know the answer. Yeah.
I think it's not a good time to stop. Parts of being an organizer.
Yeah.
So semi-metals are very robust states, and a Dirac
Right.
cone also can be fixed by charge neutrality to really sit at the
Right.
chemical potential. But as you formulated your supermetal is very finely tuned.
Tuning two parameters, yeah.
Have you thought of any way that might make it look more robust?
Right.
Any conditions that might pin that?
Yeah. So there's only one case I know, which is if the system has some particle Hove symmetry. In that case, you can get a high order by Hove singularity at the Fermi level without any fine tuning, right? And this occurs in the case when the dispersion is k to the third power. This shown here, yeah. Right. So let me move to. So I think generally speaking, if you have a Van Hove singularity with an odd power of where dispersion is the odd power of k, then particle Hove symmetry fixes it. So no other perturbation will be allowed by particle Hove. Sorry. Yeah, here, right. Yeah, right. So, right. So here, for example, this term in the brackets defines the high order Van Hove singularity, but there are all other perturbations. But if there's a particle Hove symmetry, if we require energy at k and minus k are opposite, then all these even powers of k terms has to vanish. So then we are left with a high order Van Hove singularity right at the Fermi level. And in particular, this is how we stumbled upon it, is that if we play with, for example, a model of Majorana fermions on the triangle lattice, and the simplest type binding model you can write down has this high order Van Hove singularity without any fine tuning, right at the Fermi level, because Majorana fermion spectrum is particle symmetric.
You don't know something that involves conventional Fermi?
I don't know, yeah.